This is another in the series of the large plates of the Earth, tectonic plates of the Earth, the South American plate, 18th of February 2022. This is a tectonic map of the South American plate, outlined in red on the right-hand side and in blue on the left, being top and bottom. That actually implies that the right-hand side, which is the Southern Atlantic Ocean, is a spreading centre from which new oceanic crust is being developed. The left-hand side, marked in blue, is essentially a subduction zone where the Pacific Ocean floor plate regions, you have essentially transfer faults, that is lateral sliding faults, where the North American plate is sliding to the left, and in the Scotia's plate, likewise, there's a similar phenomenon. So that the South American plate is essentially sliding westward. This is another general view, cutaway to demonstrate the origin of plate movements. The plates are very thin, or the crust of the Earth and portion of the mantle that are called the lithosphere, that is rocky sphere, and sufficiently robust to be moved as a single plate. It's very thin, 8 kilometres of ocean crust and 30 kilometres of continental crust are combined with 60 or 70 kilometres of the Earth's mantle to give a zone about 100 kilometres thick, which is jostling and moving laterally based on the spreading from the mid-ocean ridges, shown in this diagram at 12 o'clock, where from deep in the Earth, essentially the liquid outer core of the Earth, some 3,000 kilometres down, a plume of heat comes up, not only as shown here going to a hotspot, but also along the linear ridges of the continental ridge, or the oceanic ridge, beg your pardon, where plates are separating. Intrusion of magma occurs, which has been derived from a heat source way down at the outer core, 3,000 kilometres below. This causes friction on the underside of the 100-kilometre thick lithospheric plates, and that would drag them apart so that injection of magma continues and the plates move away from the central ocean ridge. This is made into Earth's great recycling system. By certain locations at continental margins, one tends to get the denser oceanic crust subducting as along the Andes mountain chain, or the Andes Trench, Chile Trench sometimes called, where you have the Pacific plates subducting below the continent. So that's the pattern of the global tectonic theory, that you have oceans expanding in the central ridge and contraction and loss of oceanic crust at the margins of the continents. This is reflected in the earthquake patterns, particularly along the Andes, which are a type example for a subduction margin, an Andean margin as they're called. And you'll notice that the plates doing the subducting here are the Caucasus, the Nazca, and the Antarctic plates. These are the eastern half of the Pacific, which median ridge actually runs off this diagram in the north, runs into the Gulf of California, of course, and is completely overridden by the North American plate. South American plate has not ventured so far, but it's gone a good way across the eastern half of the Pacific Ocean crust. There's only half of these plates, Cocos, Nazca and Antarctic plates, are now evident, the rest having been subducted below the continent. So the deepest earthquakes shown in yellow, then blues, purple and red, and these are demonstrated in a cutaway diagram to the right, where we see the earthquakes around 100 kilometres depth are the yellows and reds, particularly yellows. Repeating that, particularly yellows and reds, and that's why you have two zones of volcanism essentially in the Andean plate, in that the deeper earthquakes to the east, although they would cause shakes in the central mountain zone or the eastern mountain zone, they're not so prone to volcanism, where the red and starter blues are about 100 kilometres depth, at which melting of the subducting plate occurs, and the magma rises to give the lines of volcanoes that run along the western margin of the Andes in particular. This diagram also illustrates the boundaries between the Cocos and Nazca and Antarctic plates, spreading centres that define new ocean crust formation with lesser but shallower earthquakes inside 100 kilometres depth. The Threads, the Andes, are the type example of a subduction margin where the plates of the eastern Pacific Ocean crust, that's Nazca, the Cocos and Antarctic, well, the Cocos doesn't strictly slide under South America, and they slide eastward beneath the continental crust of South America. And they slide in at the Peru-Chile Trench, also known sometimes as the Atacama Trench. It's about 160 kilometres off the coast. It reaches a maximum depth of over 8,000 metres and approximately 6,000 kilometres long, with a width over 60 kilometres. There are 4 seamount ridges shown here with yellow arrows, which occur within the Nazca plate, and they enter the trench. They're all named, and north to south the Carnegie, which comes from the Galapagos hotspot, the Nazca, Iquique, and Uenda Fernandez ridges, all arrowed in yellow. They arise from hotspots over which the Nazca plate has moved, and therefore carried away the edifice of the volcanoes from the hotspot, which is always constant position, and it gives you this line of extinct volcanoes running in the direction of plate movement, the oldest being furthest from the hotspots, which are essentially off this diagram. And the Peru-Chile Trench is filled with over 2 kilometres of sediment, which creates a relatively flat bottom topography. And in the south there, the Chile Rise, which is the mid-ocean ridge between the Nazca and Antarctic plates, is being subducted under the South American plate. It's oceanic crust sliding in under continental crust. And there's another picture showing the Amazon drainage away from the Andes and the broadening of the Andes in Peru. Indication there on the right of the 4 ridges of submarine extinct volcanoes, with the Carnegie in the north coming from the Galapagos, and an indication with the black arrows in that right-hand diagram that the movement of the Nazca Plate is of the order of 6 to 7.5 centimetres a year. That is, it's subducting 70 kilometres of ocean crust. It's subducted every million years. There's a small plate which causes an aberration in the volcanic chain. The active volcanoes are shown there as red triangles. And although earthquakes continue, there's a complication on the simple version just north of or in the bump of South America. And reading the bottom, 4 seamount ridges resulting from hotspots within the Nazca Plate enter the subduction zone along the Peru-Chile Trench. When we say the hotspots are within the Nazca Plate, it simply means their location is constant and the Nazca Plate has moved eastwards across them, carrying away the extinct volcanic masses. Here's a cutaway diagram of the principle. Out on the left-hand side, we see incidentally, there's a huge contraction of scale in the vertical here. If we think of, see in the middle, 2,800 kilometre line from the molten core to the base of the crust, or the base of the lithosphere, really, which is the dense portion of the mantle and the crust, about 100 kilometres thick, that is being moved by the convection currents. And that one on the left is the main separation of the Pacific crust, Pacific oceanic crust. So the Pacific Plate lies to the left of that line, where the rift volcanoes are marked. That's the ocean ridge or diverging margin of the Pacific Ocean, and the Pacific Plate lies to the left, the Zagros to the east, and the Atlantic to the east also. So in the middle of the northern of those two plates, there are a series of hotspots. 5 trains of extinct volcanoes have been carried away by that eastward movement of the plate. And that's again a hotspot or a plume of heat rising from the outer mantle and developing outer core and developing magma at the base of the lithosphere, about 100 kilometres down. It's shown there as 70 kilometres. So we're asking you to note a scale change there, and the subduction trench is clearly defined, rising magma from about 100 kilometres depth, because the good deal of water is taken down with the subducting slab. This lowers the temperature at which melting occurs, so you get a magma developed at about 100 kilometres depth, rises under gravity and intrudes as volcanoes, and you get the typical stratovolcanoes of andesite. That's more or less halfway between a basalt and a granite in composition, not as much silica as the granite, and intermediate, therefore, in composition. Basalts having practically no free quartz. And this is a more viscous magma, which than basalt doesn't flow in great sheets, stays close to the eruption conduit, and often assists in building these cones of the stratovolcano, because you get alternating layers of ash and rather viscous magma, rather viscous lava. And just reading the notes underneath, the subducting plate slides in at a shallow angle under South America, and this results in a very wide zone with 2 chains of mountains and an intermontane valley system, the altoplane between them. This is a tomographic study, or earthquake waves can be studied in much the same way as we examine the interior of the human body. Organs can be identified in that way, so can the subducting slab, because of its different density. Montane valley system, the Altiplano. So tomographic studies of the earthquake paths, that is based on their arrival times at different locations, has led to 3D presentation. So there's that zone of really significant width to the Andes, several 800 kilometers or so, Peru. Good look there at the Amazon Basin, showing quite green, and some of the older cratons of Brazil standing proud in the east. That's their rocks over 2.5 billion years, many of them. Some of the old cratonic or stable areas of South America. This, of course, contrasts with oceanic basaltic rocks, where none are known really over 200 million years. An astronaut photo across that broad zone of the Andes, with the high plains of the Andes Mountains in the foreground, and the eastern range with its young volcanoes facing the much lower Atacama desert of the Altiplano. Here's a plate diagram, tectonic diagram of the plates. The western section is the huge Pacific plate, one of Earth's large plates, but there are little tiny plates at the north, the Galapagos, halfway down, and yet another in the south. It's a Juan Hernandez plate. Just small rotational plates being formed as a result of the interaction of the Pacific and Nazca plates. The Nazca is now moving away from that central expanding ridge at about 40 millimeters a year, or 40 kilometers every year, up to 53 in the south. Clearly a rotation on it where the south is moving a little faster in a easterly direction, and is the northern part of the plate. And the Cocos plate separates more rapidly, nearly 70 millimeters a year, towards the subduction zone under the Middle Americas. There's a small plate, the North Andes plate, which is essentially under compression, but broken off from the South American plate in the far northwest of the continent. And there's a separate unusual plate of the Altiplano in the mid-zone of Peru. So the blue line running down the west margin is the Chile Trench, Atacama Trench, whatever you like to call it. And the subduction there of the Nazca plate is going on eastwards at a rate of 50 kilometers or 40 to 50 kilometers every million years. And to read that section on that plate, the Atacama, the Ecuador highlands, are also called the Interandean Valley region. There's a western and eastern Andean range with a depression in which most of the cities are located. For example, in the case of Ecuador in the north there, it's the city of Quito. there's two areas shaded in grey, which indicate regions that are undergoing effectively orogeny or mountain building or extreme faulting and tectonic unrest, as it were, currently. So if we have a simplified block diagram of the Peruvian, or if you wish, Ecuadorian area, have a western Cordillera and an eastern Cordillera with the Altiplano between them. And then the front of the Andes in the east gives way to the broad Amazonian plains. And so elevations marked there give an indication of altitudes. And the subsurface shown in the cutaway section with continental crust showing the sub-Andes out in the central region being thrust eastward. The little black lines are faults, the back thrust in the eastern Cordillera. Two chains of volcanic activity there. This tends to show the Nazca slab as reasonably steeply dipping, but it fell off at a much steeper angle beyond this point to the east. There are two zones of volcanism there, one in the western, one in the eastern Cordillera, shown by the red. And then the Nazca slab, oceanic crust sliding in to the east. Yet another diagram, cutaway diagram. In fact, this would be illustrating more particularly the upper crustal structures where there's some what we call shallow deformation or thin-skinned deformation with thrusting to the east, which I've outlined with little black lines. You see a line of white earthquake epicenters there, or focused foci running across from the lower crust. That's a slippage fault that has developed, shearing its way eastward. And below that, there are various blocks recognised within the crustal zone or lithosphere of South America, shown in the orange and dark green, where the blues are the subducting belt of the into the asthenosphere or deeper part of the crust. Then there's perhaps underneath an enlarged version of these faults within the shallow thrust belt, and the black outline of the subducting zone. Just to read this, the Nazca plate is subducting at 50 to 66 millimeters per year under South America. And just remembering that converts to kilometers in a million years, 50 to 66 kilometers every million years, which is reasonable geology time to talk about. Note the earthquake foci and the shallow thrusts at about 25 kilometer depth that help to define the geomorphology of the Altiplano in particular, and in the far eastern section of the pre-range area. And the granites, the coastal range and the eastern Cordillera, and also the volcanics, and that includes the Machu Picchu region, range in age back to 250 million years old. So this subduction has been going on for a very long time, much longer than the oldest known ocean floors of today. This is the region of Chile where things happen. Notice how there's a bit of complex arrangement between the states, Paraguay, Brazil, and Argentina meet there in the eastern portion of the continent, and that's where the famous Iguazu Falls, a huge range of waterfalls, occurs in the basalts, I think of Cretaceous age, over 100 million years old. they probably relate to the early breakup of the Atlantic Ocean, which is reflected by volcanic rocks and certainly other igneous rocks all around the Gondwana region. Chile Trench is outlined there a long way offshore, and we don't see clearly defined the western and eastern mountain sets within the ranges there, but it's a very clear break for the plains of the east section of South America. Santiago and Buenos Aires in the south. This is a picture of how Gondwana looked a couple of 100 million years ago. Those darker browns are the older cratons, the more stable masses, where rocks are older than, many of the rocks are older than 2.5 billion years. So it's a bit like those ice flows where the older ice is incorporated in younger ice, and then new leads occur between them as the continents break apart. And so there's the very early stage of fracturing, probably of the order of 200 million years ago, where it would have been a huge rift valley like the East African Rift Valley today. Herds of dinosaurs probably roamed the plains, but where that fracturing occurred, the significant thinning of the crust and later subsidence as a result of its a bit like a thin piece of wood sinking lower in the water than a thick piece of wood, and you get sedimentary basins along that zone, which are very prominent petroleum producers, both in the offshore African coastline and Brazilian coastline. And we're looking at some cross sections there, both of the Santos Basin and the sections A and B further to the south. And just to read that, the Cratonic or old blocks of Africa and South America, as they were in Gondwana, the continental breakup commenced almost 200 million years ago, and joins can be made between these rifted fragments, such as the Sao Francisco block and the Congo block, or the Rio de la Plata and Kalahari block. The geology is very similar as it is in the North Amazonia and West Africa. Sections A and B through South America. Well, section A would look akin to this, and we can see the coast suffers some faulting and intrusion, of course, coastal fault scarps, but these are the result of the friction of the block subducting or sliding in through the trench. And it gives a very characteristic subduction structure known widely as the, beg your pardon, memory slip there. The West Coast has a long history of subduction and its related igneous activity, and the style of subduction is the Andean subduction, characteristically with andesite volcanic rock. There's an example now of the eastern side, the B section of South America, where you have development of sedimentary basins in offshore Brazil due to the continental breakup. You don't see these developed along the subduction margin in the west. That's a very characteristic difference between what I describe as passive margins in the east and active margins with subduction in the west. So you've got, at the time of breakup of South America and Africa, you had crustal thinning due to the stretch between continents, and this was resulting from uplift due to a great mass of heat or thermal front rising right from the liquid portion of the core, 3,000 kilometres below, causing a huge uparching and a fracture in its crest, and then ultimately formation of magma and intrusion of magma, such that you had the separation of the continents with the margins tending to slip in by normal faulting, and sedimentation resulting from the uplift of the shoulders of those rifts. And with continued sinking of the thinner crust, sedimentation overlaps the edge of the continent, as in the bottom diagram. So here are some examples of that, actual measurements and the like. We won't look at in great detail here, but if you took it at a bit over 100 million years ago and looked at the difference between Brazil and Namibia and southern portion of Africa, you'd see at 112 million years, effectively very little oceanic crust, or none portrayed here, although the section is broken. Whereas if you took it 26 million years later, there is a significant oceanic crust included within this section, and we see that there's extrapolation of the stretching of the continental mass in brown of South America from about almost 100 kilometres, from 600 kilometres out to 700 kilometres. And that's as the oceanic crust of the South Atlantic was starting to develop. Another such diagram further north between Brazil and Angola. You see a more, what should I say, plastic pull apart, particularly of the eastern side of South America. And the sediments on both layers are deformed by salt, which is accumulated during the phase of the first opening of the rift. Invasion of the sea occurred periodically, and this evaporated to give enormous salt deposits, as you get in the South African Rift, northern portion of the South African Rift Valley. The Red Sea has periodically flooded into the Afar Triangle in Ethiopia, and there's over a kilometre thickness of salt formed there. So this salt is incorporated in the early sediments of the continental margin and often results in subsequent deformation, or deformation even during deposition of the sediments. So this is a comparison of the passive continental margins of Brazil on the left, Angola on the right, a bit over 100 million years ago. And in this case, 250 kilometres of continental crust stretched and thinned. But only a segment of the oceanic crust is shown here due to the break in section. Looking further at the coastal region, east coastal region of Brazil, as outlined bottom right with a little red rectangle. These are the offshore areas of Rio de Janeiro, misspelling. Petroleum exploration has been extensive along the east coast of Africa and very successful. And the Santos Basin in the south here and the Espírito Santo Basin to the north are just two of these many basins along the coastline. And they've been profitable exploratory areas for petroleum. Just having a quick look at what a section of them looks like. When they do seismic, that is ship towing a line of geophones, ship will provide a thump or a small explosion, and they'll record the times of reflection of those sound waves back from the various layers below the ship and get a record rather like the middle one or the bottom one of these two. And that's indicating the different intervals of reflection time between the different layers. And they can process this to give very realistic indications of the depths to various structures or strata. Perhaps we can see there's a salt dome or a little mound just off centre to the right. That's reflected by very little in the way of reflection at all of the sound waves. Same with another pinnacle of salt further over towards what is a massive, great salt wall called the Outer High. They can differentiate zones of the crust, various features in the faults, plus details of the post-drift sediments, which are not, the details not shown here, which is much more their target interest in the case of petroleum studies. The seismic reflection line across the Campos Basin of offshore Brazil and its geological interpretation. As extension thinned the continental margin crust, an early sag basin developed, you notice that in the centre, at the close of which widespread and thick salt was deposited. And that was almost so in a number of basins along the margins of the two continents before they separated to be true ocean. And during post-drift deposition on the continental margin, or both continental margins, the salt migrated down dip and accumulated into pillows and a salt wall. And the pillows then tended to rise under gravity because they're very light and very mobile, like treacle after they're under 3,000 metres of sediment, and they force their way up through the sediments to actually form islands at times, as they do in the Persian Gulf today. And there's a bit of an illustration again from the Campos Basin showing character of that salt deformation. And of course it forms anticlines or upward bowed regions of the strata, which is very, very important for the migration and trapping of petroleum. Otherwise, petroleum will just gradually seep up through the porous sediments, and provided you get a sealed cap rock going over the salt domes, that will provide a wonderful potential reservoir for petroleum products, both gas and oil. And this reads, the continental margin sedimentary basins of Brazil are marked by salt structures, generally called salt domes, that developed during deposition of the sediments in the last 100 million years from salt deposited in the early phase of rift development between Africa and South America. So you may have nearly 200 million year old salt or 160 million year old salt, depending on when it was formed, intruding into sediments of less than 100 million years, bowing them up and resulting in reservoirs for petroleum. Returning to the southern section of the Andes, we can see how broad it is north of San Diego, and how high and confined, I suppose, the trend is south of San Diego down to Cape Horn, particularly Patagonia, which is an ill-defined sort of zone of the southern Horn region of Africa. There's fantastic scenery, which I'll show in a minute, I imagine. But at the moment, I go back to that story of separation of Gondwana, where you had South America, Africa, and Antarctica separating perhaps 130 million years ago with the first invasion of oceans, and initially spreading ridges between these three continents to be would have been quite simple, with a triple point in the middle, perhaps. And today, however, things are much more complex. This diagram also shows pink patches in various areas there on each of the continental margins, and also between Antarctica and Africa, patches of pink. And these were large igneous provinces of volcanic rocks and intrusive igneous rocks, which are very characteristic of the early phases of separation of the continents. We know them, for example, from Tasmania, the Dolomites, Mount Wellington and the Central Highlands of Tasmania are part of that phenomenon. And to read this, initially the spreading ridges between South America, Antarctica and South Africa would have been a simple triple point. Today, however, it's a little more complex. To the Cape anyway, by this peculiar horseshoe plate, the Scotia plate. Complex movement to the east, but the other point, I suppose, is there's a broad ridge of extended continental crust to the north. The Falkland Islands sit there fairly sharply defined off the just northeast of the Cape Horn itself. And I'll have a section across that extended crust in a moment. But to this 3 o'clock, we can also see green transverse faults separating the Antarctic rise, mid-oceanic rise between the Antarctic plate and the South American plate. So that's where those two meet and continue round to be the central ridge of the South Atlantic Ocean. There's another diagram, looks a little bit distorted to us, but of the Cape Horn region or Patagonian region with the Antarctic plate contact with the Nazca plate, which is the Chile rise, largely extensional, looking by largely transverse, looking by the green coloration on that, with extensional zones in red displaced by those transformed faults. There's a very small Fernandez plate right up in top left-hand corner. It's undergoing rotation quite a rapid rate, 83 millimeters per year. That's the East Pacific rise, from which the main portion of Pacific Ocean crust derives its new spreading volcanism. The Antarctic plate extending right around to the south along the extended zone where the Antarctic plate is written in the bottom. You have the red spreading zone, the green sliding zones, which means that Scotia plate has been sliding eastward more rapidly than the eastward moving Antarctic and South American plates. Rather interesting that. And out to the far east there's the subduction trench of the South Sandwich Islands, sliding in where essentially South American plate oceanic rocks are sliding in under the Scotia oceanic rocks. Quite a complex zone. It's a little bit, or quite a bit similar to what goes on between the large continents of South America and North America, and also Africa and Eurasia at Gibraltar. But shortly we'll look at the similar feature in the Caribbean plate. Just to read this one, new oceanic crust of the Nazca and Antarctic plate spreads from the East Pacific rise and move eastwards as it ages. When it reaches the plate boundary, its collision with South American plate, it is subducted at the deep ocean trench, as shown. That's the blue Atacama Trench, and the Scotia, Shetland and Sandwich plates form a similar structure to the Caribbean plate. The Patagonia and areas of Cape Horn are outstandingly beautiful and dramatic. The Torres del Paine National Park was marked on the previous slide. I think it will be on another. To the east of the Andes, however, it's bounded by several sedimentary basins, huge ones like the Orinoco and Amazon Basin, and several others on the region of South America. And these separate the Andes from the ancient craton of the northeastern region of South America, which I showed in previous diagrams. Back to that South American plate, we would have, just a while ago, that photograph would have been taken on the western side of the tip where that 31 is pointing 11 o'clock on the western side of the Andean belt there. All right, well, we're looking at Antarctic plate, West Antarctic Peninsula coming in, funny little Shetland plate, extension opposed to subduction of Antarctic plate beneath itself, as it were. Or certainly the Shetland plate has broken and is subducting beneath the Antarctic plate. The Sandwich plate's a very small one there, and it's quite young oceanic rock in that. As I say, this plate is moving westward, but it's unrolling eastward. That subduction zone is rolling back to the east and very rapidly, essentially. So that it's a strange phenomenon, a bit like putting a toilet roll on the floor and rolling it across. It's unraveling to the east. Just to read what I've stated here, the South Sandwich Islands are exposed part of a volcanic island arc, which of course is related to that subduction belt of the South American plate beneath the Sandwich plate. And the East Scotia Ridge is a result of this. It's a zone of expansion resulting from the rapid subduction occurrence and rollback to the east, and hence is effectively creating a very small plate with young crust in there, less than 8 million years. So the East Scotia Ridge is an active back arc, meaning it's behind the volcanic arc relative to the subduction zone, spreading center, located to the west of this island arc, which I haven't shown, unfortunately, between them in the South Atlantic Ocean. The resulting small sandwich plate is less than 8 million years old and is the result of extension due to the rapid rollback of the trench. That's the eastward rollback of the trench. So it is a complex phenomenon, acting like a hinge between the enormous South American plate and the Antarctic plate. This diagram perhaps a little confusing even to me, but we can see pretty similar region here with Cape Horn at 10 or 11 o'clock and the West Antarctic Peninsula coming through at 6 o'clock. The Sandwich Island arc is out where the number 2 is illustrated. And if we look at that diagram 2, those are successive positions of the subduction zone over time. So each little black square on that graph line running right through the middle of the diagram indicate where it was sometime in the last 40 million years. I suppose, in fact, you can regard them as about 8 or 10 million years apart. So that subduction zone has moved over the past 40 million years across that huge stretch of ocean. But if we take other points on the arc, on the horseshoe, as it existed 40 million years ago, you see them labelled there 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, the lateral areas have tended to move away, to arc away either north or south. So it shows how complex the structure of a plate can be, even small, or particularly a small plate in this case, growing as oceanic crust and spreading in different areas. Tracking of 6 points over the past 40 million years illustrates the growth of the Scotia Plate by rollback of the subduction zone. Note the lateral movement of these back arc regions, that's on 1, 3, 4, 5, and 6. These demonstrate the complexity of the history of development of even small plates over time. Here's another illustration of pretty much the same thing. These colours represent age of ocean crust, and the simple story is present in the eastern part of this picture, or in the central Atlantic. Sorry, it's really southern Atlantic region, central portion of the southern Atlantic. The youngest crust is shown along the mid-ridge, and then symmetrical away from that, successively older bands of oceanic crust. The key is given up in the top left, so that the purplish or denser reds are the last 10 million years. The pinks go through to 33 million years, orange at 40, and then starting in greens, be about 50 to 60, getting through to 80 in the darker greens, and even 120 as you start to go into the purples, 150 or 160 million years. So that's a simple pattern of expansion for the southern Atlantic. Whereas if we look at the Pacific side, the Antarctic plate and the Nazca plate have quite broad zones of modern crust, less than 10 million years old. So they're spreading quite rapidly compared with the South Atlantic, and the zones to 33 million years are broader likewise. But in fact, there's no ocean floor older than 50 million years evident there on Nazca or Antarctic plates. That is because it's been subducted into the Earth's mantle. And there's been a relative movement between the Nazca plate and the South American plate, which has assumed a huge width of ocean crust. If we look at the little black line F to E, Falkland to Morris Ewing Bank, if we look at a cross section there, it'll show how a little bit of the continental crust shows extension. And this is a picture just to give an illustration of the complexity of densities. The relative density of sediments at the top vary between 1.8 and 5, or I think I read 1.6 and 5.3 further from land. So there's a veneer of up to 5 kilometres of sediment subsea between the two blocks of continental crust, that of the East Falklands and the Morris Ewing Bank, north of this Scotia plate that we looked at in the last diagram. And then if we look at the oceanic layers, well, at depth, their densities 8 and 7s, high 7 or 7.4. And this is the reason, essentially, that oceanic crust will almost always tend to slide in under continental crust. There's a significant break at the two types of crust. The lighter, essentially lighter continental crust is floating deeper, floating higher, a bit like a big block of wood compared with a smaller block of denser wood. And that presents a natural break when there's pressures as the result of new developing ocean. Fractures often occur in that situation, and the oceanic layers will subduct below the continental. So this is really just showing the relative densities of the sediments continental and oceanic crust in the Falklands region. If we look down there, the Falkland regions, it's actually shown as a rather white blank, indicating not much information at the time this diagram was drawn. I won't enlarge on that, but it again shows the outline of the South American plate with the spreading zone in red through the southern Atlantic, the green across the Scotia plate in the south, the blues running up for the subduction belt that runs through even the North Andean, separating the North Andean plate from the main South American plate. And then it appears into the Caribbean, or we see half of the Caribbean plate outlined, which, as I said a few minutes ago, is very similar in a way to the Scotia plate. These act like hinges between the major blocks of earth crustal material and major plates, and has accommodated the movement of, in this case, South America and North American plates. When one thinks about it, 200 million years ago, South America and Africa were crammed up against the portion of the North American coast that we can see now, so that South America essentially occupied the Gulf of Mexico, and the African plate was against Georgia or somewhere on the southeast coast of the United States. Here again, too, we can see the relative rate of expansion of the Pacific Ocean has been significantly greater than that of the Atlantic. Just check the width of the yellow bands, 10 to 50 million years, much more oceanic crust in the Pacific than in the Atlantic. Same token, the mid-ridge where this is being derived in the Pacific has gone into the Gulf of California and been overridden in the region of the San Andreas Fault. So a little bit on the Caribbean region. This is the join of the North American plates and the South American plate. And that black line at the top of the curved oval line essentially encompasses the North American plate, whereas the South American plate is inside that red arc in the southeast corner of the diagram. Okay, the zone of separation clearly is complex, and in the case of the North American plate, largely sliding north block west, the North American plate going westward relative to the Caribbean plate. But there is a subduction zone continuing where the Cocos plate is disappearing under Middle America, in the Middle American Trench. Likewise, the Nazca plate is slipping in under the South American plate in the south. There is a hot spot at Galapagos, which is complex because there are two zones of extinct volcanoes moving away, two ridges, one on the Nazca plate, one on the Cocos plate. Suggests that the dividing ridge between the two was further south at one time. I won't discuss in any detail the Little Panama plate, or even for that matter, the North Andes plate, which are the two that separate the Caribbean from the South American plates. But looking at the Caribbean plate, it marks the southern boundary of the North American plate, that subduction zone under Mexico in the west, where the Cocos plate slips in at 67 millimeters a year, and then some spreading across continental material, but largely lateral movement with north block west. That's left-hand movement, as I would describe it, or anti-clockwise movement, runs right across to the Lesser Antilles subduction zone in the east, where there's 27 millimeters a year of the South American plate sliding in under the Caribbean. Then there's more lateral movement, this time clockwise or right-handed, with the South American plate moving west faster than the Caribbean. And so it goes on across those southern plates of the North Andean and Panama plates. A bit complicated in detail, but they're being rotated by virtue of the movement of these major masses of the North American and South American plates. In the 3 o'clock position, the transform fault goes off the top of the Caribbean plate, and then becomes a spreading centre locally until it extends across as a major transform into the central Atlantic region, where it heads north to the North American plate, south for the South American plate boundary. So that zone there, marked as a tectonic zone of crushing and much faulting, is the boundary between the North American plate and South American plate, the only region in which they're actually in contact. And the Caribbean plate has had a similar history to the plate we discussed, to the South Scotia plate. It originated over near the Cocos plate and has rolled back. That subduction zone in the east of the Lesser Antilles, which has of course, the Lesser Antilles are volcanic islands which lie to the west of that subduction zone, where that subducting South American plate has reached about 100 kilometres depth. So you get a volcanic island arc in the centre of that horseshoe. Well, that belt has moved from the region of the Cocos plate in the west there across to its present position over a period of something like 40 or 50 million years. The Caribbean plate formed at the Pacific and drifted relative to the Americas towards the east, although its motion is actually 10 millimetres per year to the northwest. That's a little hard to visualise, but that's the movement of the plate currently to the northwest, but its growth has been eastward. And as you can see, by fairly rapid subduction of 27 millimetres a year at the position at 3 o'clock under the subduction zone. I don't know whether I need repeat too much of that, but look at this diagram and it shows the whole of that region, the Pacific plate in the west, separating from the Cocos plate. So you've got a new ocean forming there, but this plate being destroyed, the oceanic crust sliding in under the trench of the Central Americas. Caribbean plate and its complex development with subduction in 2 locations at least, one by the North Andean plate, another by the South American plate, giving that volcanic arc of the Lesser Antilles, marked here as a red blotch. Also, minor subduction of the North American plate at the top end of that horseshoe, with the zone of orogeny or strong faulting and deformation going on around the North American, South American plate boundary contact that extends out into the Atlantic Ocean. Reading that, the Cocos plate is expanding northeastwards and being subducted beneath the Mexico and Central American regions. The margin of the South American plate with the Caribbean is for the most part a transverse fault, with a rapid subduction in the east, where oceanic crust of the South American plate is being subducted beneath the Caribbean ocean crust. The small North Andes plate has complex interactions with its neighbours. And this is a picture just showing how much complexity and interaction there is. These are earthquake epicenters. And the colour is indicating the depth to the foci or hypocenters. The reds are shallowest, grading through orange to green, finally to blues where they occur locally, particularly apparently on the North Andean plate, contact with South America. But the best pattern for this is probably seen where the Cocos Plate is sliding in under Mexico City, so that at 100 to 150 metre depth, you've got a lot of green and yellowish epicenter foci in the vicinity of Mexico City, not marked there, but southwest of the Yucatan Peninsula. Large earthquake, large green one at 100 kilometre depth. And of course, there's a whole series of active volcanoes in and around Mexico City. And the black arrows indicate directions of movement on those transverse faults at the North American Caribbean plate boundary. And again, between the South American plate and the Caribbean plate or North American plate, depending on which portion we're looking at the very northern portion of the South American continent. Perhaps as a final summation, we look at one of those very general diagrams again of the entire South American plate. It's more than half oceanic crust of the South Atlantic Ocean. Doesn't include the Scotia or Caribbean plates, of course, nor really the North Andes plate, although that's been an integral part of the continent for a long time. It's not strictly part of the South American plate at the moment. The subduction zone down the west and the expansion zone around the east. So that's the general story of the South American plate. To summarise, the eastern boundary from the Caribbean to the Sandwich Islands is a South Atlantic spreading ridge. The southerly edge is a complex boundary with the Antarctic, Scotia and Sandwich plates. And the westerly edge is a convergent boundary with a subducting Nazca plate. The northerly edge is a boundary with the Caribbean plate and the oceanic crust of North America plate. On that score, we'll probably close this session on the South American plate. Thank you.